Good morning, everyone. My name is Revan, and today I will presenting a talk on one of the most exciting frontiers of modern physics and computing: quantum networking. This topic lies in the interaction of quantum mechanics, information technology, and communication system. It aims to revolutionize the way we share and secure information across the globe. Now we are going to next slide. What is quantum networking? To begin with, what exactly is quantum networking? Quantum networking refers to creating a network that uses the principles of quantum mechanics, such as superposition and entanglement, to transmit information. Unlike classical networks that use bits, which can either be a 0 or 1, quantum networks use qubits or quantum bits. A qubit can be 0, 1, or both simultaneously thanks to the principle of superposition. The ultimate goal of quantum networking is to connect quantum devices like quantum computers and quantum sensors to enable distributed computing and ultra secure communication. We are going to next slide. Quantum networking is built upon three fundamental principles of quantum mechanics: superposition, entanglement, the no calling theorem. Superposition. This allows PIP to exist in multiple states at once, increasing information capacity exponentially. Entanglement. When two or more waves become entangled, they share a linked state. Measuring one instantly determines the state of the other no matter the distance. This property is key for quantum communication. The non-cloning theorem. It's impossible to make an identical copy of an unknown quantum state. This is why quantum communication is inherently secure. Any eavesdropping attempt can be detected immediately. Now we are going to next slide. Building blocks, bits and quantum channels. Now let's move to the components that make up a quantum network. The first building block is FIPD. For communication purpose, FIPD are often implemented using the polarization of photons. Tiny particles of light, since they travel long distance easily. For storage, stationary waves in solid state devices act as quantum memory. Next are the quantum channels. These are the mediums through which waves are transmitted. They can be optical fibers, ideal for short to medium distance for distances or free space optical links such as laser through the atmosphere or even satellites used for long distance communication. Now we are going to change the slide. The challenge: signal loss and decoherence. One of the biggest channels in quantum networking is decoherence. When a wave interacts with the environment, it loses its quantum properties. Superposition and entanglement, a process known as decoherence. Another issue is photon loss. In optical fibers, photons can be absorbed or scattered, weakening with signal, unlike classical signals, which can simply be amplified. Quantum signals cannot be copied or boosted due to the non-cloning theorem. This poses a serious limitation on how far quantum information can travel. We're going to next slide. To overcome this, scientists has developed what are called quantum repeaters. These are special devices that extends the range of quantum networking without violating quantum laws. Instead of amplifying the signal, quantum repeaters establish entanglement between adjacent nodes, and they use a process called entanglement swapping to link those nodes over long distance. They also use entanglement purification to improve the quality of shared entanglement. This concept is the quantum equivalent of classical repeaters and is crucial for building large-scale quantum network. We're going to change the slide. Applications of the quantum networking. Now, let's look. Now, now let's look at some fascinating applications of this technology. First, quantum key distribution, simply called as QKD. QKD allows two parties to share encryption keys securely using quantum states. If anyone tries to intercept the key, the act of measurement itself distributes the quantum state, alternating the use. Second, distributed quantum computing. This involves linking smaller quantum computers to act as a signal, more powerful one, thus overcoming current hardware limitations. And third, quantum sensing. By linking distance quantum sensors such as clocks or atomic clocks or magnetometers, we can achieve unprecedented precision and sensitivity in measurements. Next one, quantum internet networking, the quantum internet. This page is described about evolution is the quantum internet. This global vision aims to interconnect multiple quantum networks, just like our classical internet connects computers today. It will require standardized protocols similar to how TCP/IP works in classical networking to route entanglement and manage quantum data across devices. Importantly, the quantum internet will not replace the classical one. Rather, it will coexist and complement it. It will enable new capabilities such as global quantum, key distribution, and large-scale distributed quantum computing. Next one, the road ahead, current status and future steps. Currently, we already have a pilot quantum networking in operation. For example, metropolitan area quantum networks or QMANS are functional in China, Europe, and the United States. Satellite-based quantum key distribution has even demonstrated intercontinental communication. Future research, future research focus on developing partial quantum repeaters, building a stabilized quantum network stack, and scaling up the number of quality of quantum memories. While challenges remain, the progress so far is promising. Next one, comparison quantum versus classical networking. Let's compare classical and quantum networking briefly. Classical networks use bits, quantum network use qubits. Classical system depends on the application. Quantum system rely on the entanglement swapping. Classical security depends on mathematical encryption, while quantum security is guaranteed by the laws of physics. In short, the quantum networks represent a leap from digital communication to a fundamental new paradigm communication based on the principles of quantum mechanics. Next one, the conclusion. To conclude, quantum networking is still in its early stages, but the progress is remarkable. We are moving towards a future where quantum computers, sensors, and communication systems are interconnected in global quantum internet. Realizing this dream will require collaboration among physics, computer scientists, and engineers. The major hurdles like decoherence and quantum repeater development are being actively addressed. Quantum networking truly represents the next revolution in how humanity communicates and process information. Thank you all for your attention. I hope this session gave you clear understanding of how quantum networking works and its immense potential for the future. I'd be happy to make any questions.